proved by mathematical induction, the sum from r(1) to n of r squared is equal to n plus 1, 2n plus 1 over 6. In a previous video, we already used a direct approach to this, and so now we're going to use what's known as the principle of mathematical induction. Mathematical induction doesn't require you to know the result. So the proposition is from r to 1 of n of r squared. If we write out a few terms, that will be 1 squared plus 2 squared plus 3 squared plus n squared, and that will be equal to the sum, which is n plus 1, 2n plus 1 over 6. We prove true for n is equal to some value. We'll usually take the first value, which is 1. So on the left-hand side, we get 1 squared, which is equal to 1. On the right-hand side, we need to put 1 into this instead of n. So it's 1 plus 1, 2 times 1 plus 1 over 6. That gives you 1 times 2 times 3 over 6. 2 times 3 is 6. 6 over 6 gives you 1. We've got agreement. Therefore, the result is true for n is equal to 1. Now what we do is we assume true for n is equal to k. So we've got 1 squared plus 2 squared plus 3 squared plus k squared is equal to k plus 1, 2k plus 1 over 6. And we prove true for n is equal to k plus 1 by adding the k plus 1 term to this side and to this side. So we get 1 squared plus 2 squared plus 3 squared plus k squared plus the next term squared, which is k plus 1 squared, is equal to the sum, which is the sum of the bits in black here, and then we need to add in order to keep the balance, k plus 1 squared. Right, we now play with the right hand side. So making a common denominator, we get k plus 1, 2k plus 1. We need to multiply this by 6 plus 6k plus 1 squared. Rather than multiply out, we can see that we have a common factor of k plus 1. And we now have left k times 2k plus 1 plus 6, and we still have another k plus 1 there, all over 6. So we've got k plus 1, so we multiply out the bracket, we get 2k squared plus k plus 6k plus 6, all over 6. Put those two terms together, we get k plus 1, 2k squared plus 7k plus 6 over 6. Now we now need to factorise this. Now if we assume that we got it right, then we should know that the factors are going to be, if we put k plus 1 here, we're going to get k plus 2. And if we put k plus 1 here, we're going to get 2k plus 2 plus 1. So it's 2k plus 3. So we can see that this factorise is k plus 2, 2k plus 3 over 6. And I did a little bit of a cheat there, but if I do k times 2k, I get 2k squared. I get 3k plus 4k, which makes the 7k, and then 2 times 3, which makes the 6. So the result is true, because we can compare this by, if we put k plus 1 into this is what we would get for n is equal to k plus 1. And therefore, don't forget to write down the conclusion. The result is true for n is equal to 1, and if it's true for n is equal to k, it is also true for n is equal to k plus 1. Therefore, the result is true for all n belonging to z plus by the principle of mathematical induction. So the positive integers, what we mean. So what we are saying, if it's true for n is equal to 1, then it must be true for the next value, because if k is 1, the next value will be 2. If it's true for 2, then it will be true for 3, and then so on for all positive integers. Okay, this has been a video to show you how to find the sum of all squares by the principle of mathematical induction. I hope you've understood, and I thank you very much for watching.